degrees of freedom here is 5. Alpha is 0.01. So then 0.01 and 2 tails. Now real quick, just to give you a bigger perspective as to why this is set up this way. The next chapter we'll do after this test tomorrow is going to deal with testing claims. So if I said, I think the average is more than 40, how many sides of the picture are you interested in? I think it's more than 40. You're only interested in that direction. That would be a one-tailed test. If I said, I think it's different from 40, that could be either way, that would be what's called a two-tailed test. So right now, it doesn't make sense as to why we have both of these stupid rows, because confidence intervals always make frickin' two tails, right? Just to let you know, there is a reason these both exist. This chart is used for more things. So on this problem, the first one, 0.01, so I look 0.01 and 2 tails, because it's a confidence interval. It always makes 2 tails. And then I want to stop at 5, 4.032. So just remember, we already did this problem. So here the degrees of freedom are 100, 90%, so what's alpha? 0.10, I like it, so 0.10 and 2 tails. And I stop at 100. So I would use 1.660, which is a little bit bigger than normally the 1.645 I would have used if I would have been able to use the z-score. So 1.660. Bam! And then we get to this freaky dude. Right? Stay with me. You got your old school freaking stuck in the mud stats teacher who for some crazy reason uses charts. Technology would give me exactly this t-score and I don't give a shit. Because you don't learn much from pushing the buttons. Some guys like, I don't care. I care. It's too bad. So I would accept 2 different things here. You either always take the bigger t-score. So the question is, do you round up to 100 or take 90? You do 90. Because any time, in fact, why did t-scores exist? Hello, you guys. Why were t-scores invented?
They're supposed to be a little bit bigger than the t-score.
In the cases when I only know S, not sigma. I like it, right? So it's a penalty in a way. It's penalizing me for not knowing something. So the problem says, yeah, you can still do this shit. You can still make an interval, but it's going to be bigger. Too bad for you, and you got to live with it because there's something I don't know. And we're like, cool, I can still do it. I'm cool with that. So here, anytime there's something you're not sure about, you have to kind of penalize yourself for it. So I'm going to use 90 because that would make the t-score bigger, a little penalty. Or if you're really, you can kind of average the 2 of these together. That's cool too, to get 95. But in general, I would say take the one that makes the t-score bigger. So what was alpha here? 0.02. So I know I'm going to use this column, and I'm going to stop at 90. So I'd use 2.368. Or you could split the difference between these two and use 2.366, that'd be fine. Okay. So I'd use 2.368. Bam.
So if you get 95, you put 90.
Yes, you always go, yeah.
You go 100?
No.
Okay.
So once you get to like 99, you might as well use the 1 for 100, that's fine.
Okay,
Right?
so
But in general, you should make the t-score larger, which means going up on the chart, right? Means going down degrees of freedom. Okay. Now you guess, you know now. So number 2, which one was it that you couldn't do? Because it didn't say, I mean, that anybody could do. Now that you yourself. See, it didn't say it was normal and the sample size wasn't big enough to save it. So this one I like to make, but can't be done. Why can I do this one? N's not bigger than 30.
Populations.
But it says it's normal, so I don't need N to save my ass. N can be anything it wants to be because it said it was normal already. So I'm allowed to do something. Beautiful. So make sure it's normal. It tells you could do you could do something. Now which thing can you do? Z or T? Why Z? Because I know this. That's it. Is it normal? You could do something. Which standard deviation you know tells you to use Z or T. So I always have somebody tell me, I know the standard deviation, so I can use Z. Not good enough. What's the standard? There's two types. Which type do you know? T-scores were invented when I don't know sigma, right? To be used when I don't know sigma. All right, I like it. And here I do know sigma. I don't need to use a T-score then. So I just have to get the Z-score. What is alpha? 0.10. And then, so I'm going to use this chart because I'm crazy. T-score chart, 0.10. But I'm just going to make sure that I go all the way. And there's that 1.645 we've seen before. So I'd use Z equal to 1.645. Kick ass. That's the Z-score I would use. Right? That's all I asked for was to find the appropriate score, find the T or Z score. I didn't give you enough information to actually make a confidence interval. What about this guy? It says it's not normal. But and what does N greater than 30 mean? That is normal enough, yeah. Okay, look. Here's the thing. You ready? No. Population isn't normal. It's just like the ages in Florida. The population of ages was not normal. When I recreate the picture using groups of 39, it will become normal. So if the population already is normal, then any groups I pick are going to follow a normal curve because they're coming from a normal distribution. If the population is not normal, that's when I need my sample size big enough so that it does become normal enough. Just like the ages in Florida. Kick ass. So, I know I can do something. What is it I can do? What is it that I have to use? T-score. Why? Only know S. I don't know sigma. Good. So my T-score. So my degrees of freedom is 38. My alpha is 0.02. Okay, now I know. So alpha is 0.02 tells me which thing to look at, which row, which column, and then I stop at 38. Wow. 38, so 2.429 it looks like. Is that all right?
Yeah.
Yeah, okay. And now if we got what, 2.429?
If we just write that answer, are we marked down? If we just write
Almost every problem we do will have to have something from you telling me why you can do something and which thing you can do. Yeah. And what's kind of nifty about this one is it's already normal, but the sample size was ready to save me if I needed it. I'm like, I'm cool. I don't need you. All right, whatever. But what do I use? Z or T? T. So population normal check. S is the only thing known. I got to use the T-score. So that means two things. What's my degrees of freedom?
0.0.
And what's my degrees of freedom? 60. What's my alpha? Okay. So my alpha tells me which column to look at, 0.01. And my degrees of freedom tells me where to stop. Yeah, 60. 2.660. Okay, so let's do a problem that we construct a confidence interval using a T-score, and I want to show you constructing is the same as z-scores were. I'm just going to put the different number in there, right? So here's what it will look like. I'm going to need your assistance. Saw somebody now. No. So let's say I have a normal distribution, and I pick 8. I don't know. Instead of ages, normally distribution of ages, and I pick 8 ages, and I get these ages. Is it 1, 2, 3, 4, 5, 6, 7, 8? That was scary, Jeff. And I want a 90% confidence interval for the true mean age. So a really good place to start is, what formula am I going to use? What situation am I in? Am I allowed to do something? N is only 8 here. Holy shit. But I told you it's normal, so I can do something. So first thing, normal, check. Second thing, which score can I use? Why Z? I don't care. Sorry. Why were t-scores invented for when I only know S? Now, do I know any standard deviation right now? No. Can I get a standard deviation?
Yeah.
Yes. What is it going to be? Sigma or S? This is a sample. It's going to be S. Now, you got to be really careful. You know already when you put it in there and you do 1 var stats, the calculator is going to say sigma equals and S equals. You don't go, well, I know sigma, Jeff. No, you don't know sigma. You don't choose that one. We're the humans. We know we put a sample in. Poor little calculator's like, I don't know, here's both. You're like, S. I need S because it's a freaking sample. You with me? A little bit? So do it. Put it in the list 1. So do some 1 var stats. I know I'm going to use, S is known, not sigma, so I got to use X bar, give or take, T, S over square root of. I know N. Yay! But I don't know S, and I don't know X bar, and I'm going to have to look up T in a minute, but let's get S and X bar first. Let's make sure you can still do that. So put those in the calculator and see what we get. If you forgot how to do this, it's a good time to remember, because I'm going to do this to you tomorrow. So you got to know how to do this. If anybody needs calculator help, this is the time to ask. Where do I go? Stat? Cal? Or stats? So now I know X bar is 30.625. S, see it says sigma? In fact, something I want to point out to you that I haven't pointed out yet. You see how it says SX and sigma X? Yes, you do. All right. And remember, when I take a sample and they got to change the standard deviation, it becomes sigma X bar, right? So I love that this is like standard deviation of individuals. When I take a group, it becomes standard deviation of a mean of things. So we normally don't put the little subscript X, but that's why the calculator does it. It's saying this is for the individual things you put in me. This is the spread. So we can't use this dude, right? We can't. You got to use this guy because it's a sample. So let's see. S is 11.426. And how do you find the t-score we're going to use? Yeah, what's alpha? Point 10, right? And degrees of freedom is 7, right? 1 less than 8. So go to 0.10, 7 degrees of freedom. I'm going to use 1895. 1.895. Another big mistake people make, a little mistake, is they'll put a 7 here, but N is 8. You can understand why somebody might put 7 there because they made it degrees of freedom, but N is 8. Yes? Degrees of freedom? Degrees of freedom is always N minus 1. Yeah. You need to be careful. It is that so far. There will be other degrees of freedom that we'll learn later. But right now it's N minus 1. And now it's just the same. I really want you guys to see how the formula work is exactly the same as before. I'm just putting a different number here than a Z. I'm not using a Z-score, I'm using a T-score, but who cares? It's basically the same problem. So I got this for my error. So 30.625, give or take this much. So I do my weird little thing, store that in X, 30.625 minus X, and then plus X. Combine it. So I get 22.97 up to 38.28. Is that evidence that this population has an average age below 40? Because the whole confidence interval is before 40. Is that evidence that this population has an average age greater than 25? No, because this has 25 in it. So it's not evidence that it's more than 25. But it is evidence that it's less than 40 because the whole interval is less than 40. It doesn't overlap with that. So this is a very basic test of a claim. I can see what my interval looks like and I can kind of get a feel for it if it's true or not. Can you guys write the conclusion? This confidence interval problem is not complete until you get the conclusion written. Oh, what's up? Sorry. Oh. this, when it says frequency list, it's if you had like an x and a p of x. So it's kind of like thinking it's its own p of x. Yeah, so that's really freaking it out. There you go. All right, so what do you guys write? ER. Yeah. 90% confident. That. Of the interval. $22.97 years. I like that. I'm 46H. 22.97 years to 38.28 years is the, or I'm sorry, contains the true mean age of this population. Yeah. I didn't really tell you where these people were from, so you can't be more specific than that. Oh, it's supposed to be the word true, yeah. Woo! Man. I sort of had something that I might not do because I get this general sense that we're pretty beat up. So I'm gonna transition into review mode. So I really, really want you guys, I know confidence intervals are still relatively new. But I hate this expression, but at the end of the day, the work I do for this kind of interval is the same work I did for the other kind of interval. I just have to use a different chart. So this is what statistics is. I told you on the first day, it's all about which formula to use when. There's little tweaks to formulas. When do I use this one? Well, the formula tells you when to use it. You gotta love that shit. Use T's when I only know S, because that's what the formula has in it. Holy crap, it's beautiful. Okay, so, does everybody have a practice test? Everybody else need a practice test? So let's make a formula sheet first thing here. By the way, on the practice test, I think the very last problem, yeah, number 9 is this kind of problem, but I give you 2 samples from 2 different populations. So it's like I said earlier, you make one confidence interval, you make the other confidence interval, and you see if they overlap. If they don't, that's evidence that the means aren't the same. It's not proof, it's evidence. So this test starts in 4, goes to 8. That's all. Just chapter 4, 5, 6, 7, 8. 4 was the one that started with this stuff. Right? Those formulas, well, when I give you x and p of x, that's when you use the formulas that have x, p of x in it. Then we got into binomial stuff. Remember this dude? And then his mean is the variation where kick your ass. That's all chapter 4. Chapter 5 was uniform distribution stuff. Nothing to write down. I told you the mean and standard deviation, I'm not going to make you do that. You guys with me? So chapter 5, you just have to know how to draw a uniform distribution, how to figure out the height, and then get areas of little rectangles. Nothing you can write down on the formula sheet. If you want to put area equals length times width, don't. It's too damn bad. Holy shit. You gotta know that. Okay. Chapter 6 is where we bring this dude back. And then we also say, well, we can do it the other way around. So if I know the x score and I want to make a z-score so I can look it up, I use that guy. If I know the z-score, as I looked it up on the chart, and I want to make it back into an x-score, then I use that one. And of course, that formula is stupid important because it's how we created all the confidence interval formulas. Let me think. And then we got this dude here. I like it. I like it a lot. Okay. Let me see. Chapter 6. Was there anything else? No. And then 7 was central limit theorem. That's this, actually. That's 7. Right? And, I mean, let's see if you guys can do this. So, the z-score never changes. But if you wanted to, look at how gross this looks. I don't know why you wanted this. So when we did chapter 7, I'm like, we took 40 women and the bone density, remember that problem, the bone density, and we changed the standard deviation, and then we made a z-score using this formula really, but this is what it looks like because I'm making a sample mean become a z-score, but the formula didn't really change. So if I were you, I might not even write this shit down. It's always mine minus the middle divided by the spread. It's just that the spread changes if I take a sample and talk about the sample mean. And then we got chapter 8 where we have 5 formulas. Ones I just had up on the board. Whew. So you only use these formulas if I asked for a confidence interval. If the problem doesn't say shit about a confidence interval, don't use these. Because that's all these do is make confidence intervals. That's what they do. And, you know, you might want to double check the formulas against the worksheets because you might be reading my writing wrong. If you write the formula on the sheet wrong and you do the problem wrong, you're going to lose points. I'm sorry, it's just the way it is. So just make sure the formulas you have are correct. So let's see, if I were you, I might try to do number 9 right now, since that's the last thing we just did today. It's up to you. Or if you've already tried some of this out and you have questions, you can feel free to ask. I have the answer key I'm going to give you in a little bit.
You do number 6. That's all.
Oh, now, so I will say this. Number 6, I do ask for the mean and standard deviation of a uniform. But that's because 6E, I want you to realize that the standard deviation still has to change to become divided by square root of it. Anyway. So everybody got all this here? Yes.
Do we not
Before I do that,
add,
hold on.
Oh, sorry. Do we not add the mean plus A over B over 2, how we did that whole thing, and then the standard deviation squared root?
So the reason I'm not going to ask you to put it on this is I'm not going to ask you that
Oh,
question on
okay.
the test. Yeah.
Okay.
In general, those are not like used a ton,
Okay.
but I want you to know they exist.
Okay.
So that's why I made you do some of the homework. That's why I put a problem on the practice test like that. I like it. So pretty cool with that. So the mean and standard deviation for a uniform probability distribution, you don't have to know that. Doesn't mean it's not important. Just mean it didn't make the cut. All right, has everybody else got all these here? You guys are good?
What did make the cut?
The mean and standard deviation for a uniform, the one that's divided by 12 and all that kind of shit.
Okay.
Yeah. I know I put a problem like that on the practice test. I don't care. It is important. It's just not used a ton. Okay, but this problem is really beautiful. That's just amazing. So everybody got all this? Let me try that one more time. Yes. Okay. So number 6 is a uniform distribution from 2 to 8. So the first few problems should hopefully be easy. So it's uniform from 2 to 8. So how tall is it going to be? 6. So when I ask you to draw the distribution, I want to see a rectangle sitting on a coordinate system with the height, right? That's what I need to see. If I don't see all that for that question, you're going to lose points. Okay, like it, because I always get somebody to just give me pieces of it or something. No. So now I can answer any probability question relatively easily. So it's probably is from 4.4 to 4.7. Yeah, so if I put it on here, so 4.4 to 4.7, this is 0.3y, so what's the area of that? 0.3 times 1/6. Is everybody with me? So uniform distribution, dear God, let the basic probability questions be easy. It is just finding little rectangle areas. It's almost too nice to believe. So it's 0.3 times 1/6, should be 0.05.